In this video, we're going to look at the next circle theorem, which is this problem here. So we have something called a bow tie inside a circle. Now, what we need to remember is, as long as we've got this bow tie, we need to remember that as long as each corner of this bow tie touches the circle, a corner is known as a vertex in maths. Now, provided we have that, we can say the following. We can say that this angle, 56 degrees, is exactly the same as this angle, 56 degrees. And that is known as the angles in the same segment are equal. So if you notice, question B says work out angle PRQ. We've just done that. And so we could say that angle PRQ is equal to 56 degrees, and the reason is that angles in the same segment are equal. That's the circle theorem. Okay, now we want to work out angle PQR. Now here is another circle theorem. It's very important. If we have a diameter, which I'm going to highlight here in yellow, yes, it's the diameter, and we know that O is the center, then it forms a right angle triangle. Now I'm going to highlight that in green, the rest of it. So we've got this right angle triangle PRQ. Then it says that the angle opposite this center inside the right angle is always going to be 90 degrees. So we could say that angle PQR is 90 degrees, and the reason for that is the angle in a semicircle is 90 degrees. And then we want to work out the size of angle POQ. Well, at the moment, it's not that obvious where POQ is. But what we can do, we can form that quite easily by drawing another radius here. And if I draw in OQ, then what I get is an arrowhead like this. We can see I've outlined in purple. Now we know a well-known circle theorem that the angle at the center is twice the angle at the circumference. Now it happens to be that angle POQ, this angle, let's just call it X, will be double of 56. So we're going to do 56 times 2, 6 times 2 is 12, 5 times 2 is 10, plus the 1, we get 112. So we could say that angle POQ is 112 degrees, and we know the well-known circle theorem that the angle at the center is twice the angle at the circumference. Try this question, pause the video, and then I'll go through my work solution. Welcome back. Okay, so what can we see? We can see a bow tie. And now the question is, does every corner of that bow tie touch the circle? Yes, it does. There we go. That's fine. So we can use the well-known circle theorem that this angle 20 is exactly the same as the angle at DBC. And that's going to be 20 degrees. So let's write that down. So the angle, or the angles in the same segments are equal. Make it really clear to the examiner that angle DBC is equal to 20 degrees. Now the question is asking to work out angle ACD. Well, Now that is this angle. Let's call that X. But what can I see? I can see a diameter here and it has a center O. Then I know that this angle must be a right angle. So let's write that down as well, that the angle in a semicircle is 90 degrees. So we could say that angle ADC is 90 degrees. And now we want to work out angle ACD. That's just going to be 180 minus 90 plus 20 degrees, which is basically 180 minus 110 degrees, which is 70 degrees. And the last part says, find the size of angle DBC. Where is angle DBC? Well, we've already done that already in our problem. It's the angle here, 20 degrees. So we can say that angle DBC is 20, and just for clarity, we can just reiterate that the angles in the same segment are equal. Just an extra clarification there. Now this question is the final one, and it's the one to be very careful of, and it catches a lot of students out. Now, if we look at this question, it's quite misleading actually. Most students would look at it and think, oh yeah, it's a bow tie, therefore it's fine. No, it's not. It doesn't satisfy the bow tie theorem, because in order to have angles in the same segment, we said that every corner of the bow tie must touch the circle. Now the problem is B touches it, C touches it, A touches it. But the issue we have here is that O does not touch the circumference of the circle. So we cannot use it. We cannot say that O and B are the same. They are not the same. But what we can say is that we have an angle at the center. And we have an angle at the circumference. Now we know that the angle at the center is twice the angle at the circumference. And also, I can use another circle theorem here. We've got a radius. I've got a tangent. Just mark them in. The radius is here, and here we've got a tangent on the bottom. So the angle between the radius and the tangent is 90 degrees. So let's write that in. The angle between the radius and the tangent is 90 degrees. So we can also say that the angles in a triangle add up to 180. Angles in a triangle add up to 180 degrees. Always state your reasons, please, in an exam. So we could state that 90 plus 36 is going to give me 126 degrees. And what we want to do essentially is do 180 degrees minus that. So we get 4, 7 take away 2 is 5, so we get 54 degrees. So it means that the angle at the center is 54 degrees. And we know that the angle to circumference is half of that. So we're going to do 54 divided by 2. And that's going to give me 27 degrees. Now, what they want to work out the size of angle AOD, which we've already, AOD, so this point is D, it should be D there. So we've already worked that out, so that's 54 degrees. And we've already stated our reason that the, we've done that already. And we want to work out angle ABC. Now we know that angle ABC is 27 degrees. Now here's the important part. that the angle at the center is twice the angle at the circumference. So let's write that a bit neater. Angle at the circumference. So at the circumference. So that's definitely one to watch out for.